Welcome to RLD Academy. In this video, we are going to discuss Fourier transform, which is one of the most important and difficult topic to student community. Here, we'll make it simple and we'll try to get basic intuition behind the Fourier transform. This is Joseph Fourier, a French mathematician. He contributed a lot in mathematics. Here, we'll discuss his two important contributions he made while he was working on heat transfer problem. The first one is the Fourier series and second one is Fourier transform. The Fourier series is applicable for periodic signals and Fourier transform is applicable for both periodic and aperiodic signals. Here we'll discuss these two topics, Fourier series and Fourier transform, in the context to signal processing. Now, this Fourier series and Fourier transform, these two are used to find frequency content of the signals. Now, I'll show you few practical signals. First one is ECG signal. It stands for electrocardiogram signal. And you can see here that how ECG signal is recorded. It is generally used to study the health status of our heart. As the heart is pumping regularly, we will get certain signal. So this kind of signal we can obtain if the heart is working properly and the heart is pumping in a regular fashion. That's how we'll get this kind of regular signals. It is called periodic signal. Now, can we find the frequency of this signal? Though it is periodic, but it is not very smooth, like sine wave or cos wave. So how to find the frequency of this signal? This is another signal, a normal earthquake signal. As earthquake occurs, we'll find lots of vibration in this wave and then it will die down gradually. Clearly it is not a periodic signal, it is a periodic signal. Now question is how to find the frequency of this signal. So this is the difficulty and we can find the answer from Fourier transform. To get the idea of frequency, first we will start with sinusoidal frequency. Consider a point P and this point is moving along this circle, and you can consider that the projection of this point on x-axis is a cos theta and projection on y-axis is a sin theta. As point P is moving along this circle and it rotates one cycle by 360 degree, thus the sin and cos theta, they are periodic over 360 degree angle. Now when point is P is here, then cos theta means cos 0 degree is 1, it will start from 1, and as its point is going along this circle at 90 degree, its value will become 0. It is coming here from 1 to 0, and then to this side it is negative, and then it will again grow and it will come to this point. It will make one cycle. So here you can understand that the sine and cos, sine is for this blue one and cos is for this red one, both are periodic and they will repeat its nature after every 360 degree angle. Now to get the time concept, we'll consider that this angle point phi is moving with constant angular velocity. So theta we'll consider as omega naught t. Here omega naught will be considering as angular frequency, radian per second. So this point is moving with constant angular frequency. So what we will get here, they will replace this theta by omega naught t. If I consider time period capital T, then after capital T, it should come to the same point here, means it will make 360 degree angle. So omega naught capital T should be equals to 360 degree. So here omega naught t is 2 pi or 360 degree. So omega naught equals to 2 pi upon capital T. Here also we can define the linear frequency, that is 1 upon capital T, because in 1 second how many cycles are completed. In t second there is 1 cycle. So in 1 second there should be 1 upon capital T number of cycles. Thus the linear frequency is considered as 1 upon T and its unit is hertz. So remember these two. The omega naught is angular frequency, that is radian per second, and whereas the linear frequency is 1 upon capital T, that is its unit is hertz. So we can relate these two. So omega naught, this is 1 upon capital T, that we can replace by f naught here, right? So omega naught equals to 2 pi times f naught. Now consider this sinusoidal wave. X of t equals to 2 sine 4 phi t. So here, if we compare this one, this is 2 pi f naught t, because omega naught t we can replace by 2 pi f naught. So 4 pi equals to 2 pi f naught. So f naught equals to 2 hertz, and its frequency is only 2 hertz. And this 2 is the amplitude. Okay. Now this is the signal that I have shown here. I have shown this signal from -4 to +4, and you can understand that this signal is having a frequency of 2 hertz, imply that in 1 second there are 2 cycles. So this duration I have considered -4 to +4, total 8 seconds. In 8 seconds there should be 8 into 2 means 16 cycles. So that you can count here. There are total 16 cycles. Now if I consider this signal 2 sine 20 pi t, so similarly we can consider 20 pi equals to 2 pi f naught, so f naught will become 10 hertz. Imply that its frequency is 10, meaning in 1 second there are 10 cycles. So in the same duration 8 seconds there should be 80 cycles. So these two, if we compare, this is having 16 cycles in 8 seconds, and here we are having 80 cycle in 8 seconds. So 5 times larger of this one. Just comparing these two, I can say that this is a low frequency signal, and next one, this one is high frequency signal. Now if I consider this signal, this composite signal, x of t equals to 2 sine of 4 phi t plus 0.5 times sine of 20 phi t, and another composite signal, if I consider 0.5 sine of 4 phi t plus 2 times sine of 20 phi t, you can notice here that these two coefficients are different. Here 2 is multiplied with sine 4 phi t, whereas 2 I have multiplied with here sine of 20 phi t. Okay, so how the composite signal will look like, that we will try to understand first. So this is the signal of this one. Now you can see that this signal is close to this sine 4 phi t. The frequency is 2 hertz. So again we'll have that kind of 16 cycles in 8 seconds. But it is not purely sinusoidal. So it's not very smooth because of the second part. The second part will contribute, and you will get some fluctuations here. Okay. So this signal, in this signal, this first part is dominating part or dominating signal. That's how we'll get this kind of shape. Now second one, you can see that second component is dominating one. So sine of 20 pi t, its frequency is 10 hertz. If this signal is dominating one, its amplitude is more, and little minor change due to this first term, then we'll get this kind of composite signal. So this is mostly high frequency signal, but little change with respect to this low frequency signal, and here it is mostly a low frequency signal, and there's a little high frequency component added. Okay, I hope you can understand this part. Now we have different problem. Suppose this signal is given. Okay, now how to find out its components? What the frequencies are present there, we want to understand. So these two components we want to extract from this signal I want to get these two components, from this signal I want to get these two components. So these we can obtain using Fourier series concept. So what is Fourier series? If XPT is a periodic signal, then using Fourier series we can expand XPT in terms of sinusoidal components. But how? How to get these sinusoidal components? Now consider A1 sine 2 pi f1t, another one A2 sine 2 pi f2t. These two signals are combined, just added. Now question is, this addition, after this addition, is the signal periodic? Okay, this is the important concept. And this frequency f1 is for the first term. F1 is the frequency for the first term, and t1 I will consider corresponding time period, and second one frequency is f2 and time period is t2. And suppose this signal is your periodic one, and that time its time periods could be capital T. Now what is the required condition so that this one composite signal will become periodic? Now this total signal will repeat if and only if both the component will repeat at the same time. So I can consider that the capital T should be integer multiple of this T1, as well as it should be integer multiple of T2. So T could be considered as m times of T1 and again n times of T2. So m and n, these are two integers, could be different. So T1 upon T2, from here we can write that n upon m. Thus f1 upon f2, and you know that f1 is 1 upon t1 and f2 is 1 upon t2. If you simplify this one, I'll get t2 upon t1. So I replace this thing, then I'll get m by n. So f1 by f2 is m1 by n, and m and n, these two are integers. Thus this ratio f1 is to f2, it is rational. So this is the important concept. So these two frequencies should be rational ratio, then only this signal will be periodic. In other words, this periodic signal, composite periodic signals can have two components, two sine waves or cos waves, but their frequency should be the integer multiple of certain frequencies. That I'll come later. So this is because I can consider f1 equals to m into f0, and f2 I can consider as n into f0, then only f1 by f2 will be m is to n, right? So f0 is called fundamental frequency, then f1 could be considered as one harmonic, and this is another harmonic. So it could be possible that m and n could be not 1, okay? It could be different from 1. Now XVT is a periodic signal I am considering, and time period is t0, and linear frequency is f0, it is 1 upon t0, angular frequency is omega naught equals to 2 pi f0. So this signal XVT could be considered as summation of sinusoidal signals, but remember that all the sine and cos waves, those should be integer multiple of the fundamental frequencies. I'll start with this omega naught. Omega naught is the fundamental frequency. So A1 cos omega naught t, A2 cos 2 omega naught t, like that, An cos n omega naught t. All cosine we can consider, all integer multiples we need to consider. Similarly, all sine components we need to consider. And we can also consider one DC term. So XPT can have all these components. It can have cosine component, cos components, or sine components, or DC terms. But remember, these cos and sine components, they should have fundamental frequency omega naught or its integer multiple frequencies. No others. So how to find A0, An, and Vn? So A0 we can easily find out as 1 upon T naught and integration of xpt, because it defines DC terms, and an could be considered as 2 upon T naught xpt times cos n omega naught t dt. So this is just to find the correlation between the signal xpt and cos n omega naught t. So if cos n omega naught t is correlated with xp, then we will get certain value of an. Okay, so this is nothing but one correlation, right? Similarly, to extract this value for Bn, we will take correlation of the signal xpt with sine of n omega naught t. And using exponential form, you can see that cos n omega naught t we can rewrite as e to the power j n omega naught t plus e to the power minus j n omega naught t by 2, because cos theta equals to e to the power j theta plus e to the power minus j theta by 2. Similarly, sine of theta equals to e to the power j theta minus e to the power minus j theta by 2j, where j is square root minus 1. So if you replace everywhere these two, sine and cos, we'll get a compact form in exponential way. Okay, so xpt we can write that in this form. It can have one DC term c0, it can have one term e to the power j omega naught t with coefficient c1, similarly e to the power j2 omega naught t with coefficient c2, like that, right side. And also it can contain this side e to the power minus j omega naught t coefficient c minus 1, similarly e to the power minus j2 omega naught t c minus 2, like that. Okay, so in compact way we can write as summation of Cn e to the power j n omega naught t. N will vary from minus infinity to plus infinity. And for this exponential form, we can extract the coefficient Cn as 1 upon T naught times integration over one time period xpt e to the power minus j n omega naught t. I have discussed and dt. So you should add these terms here, the dt. Right? So here we can easily find out this coefficient Cn. Now consider this signal. This is how the original signal, and you can see there's a vibration here, and again some small vibration is in there also. Okay, we want to decompose this original signal using Fourier series. After Fourier series components, we'll get these three components if we consider. So we can get Cn, and from the Cn we can get the sine component and cos components. So here I am just showing these three sine components. Okay, so first component is this one, very smooth, it's varying, it's 2 sine 4 pi t, and this one is sine of 12 pi t, and this one is sine of 80 pi t. So if I combine these three, we'll get this one. You can see. So if I combine these first two, then we are getting this waveform. It is similar to these things, except this one small variations, right? And if I add the last term, we'll get exactly the same one. In other words, this signal is having these three components, meaning is that if I combine these three, we'll get this original signal. So this is a Fourier series. We can easily extract the Fourier coefficients, the ck, or in trigonometric form a0, an, and vn. I have discussed this thing in detail in my previous videos. Please go through that one. Now we can discuss the spectrum of the signal. Now as this signal is having three components, one is frequency of 2 Hz because it's sine of 4 pi t, another signal is having sine of 12 pi t means 6 Hz, and it is your sine of 80 pi t means 2 into 40 means 40 Hz signals. Okay, so its amplitude is 2, so at here it's 2 Hz, its amplitude is 2. And for this signal, it is 6 Hz, its amplitude is 1.5, and last one is 40 Hz, its amplitude is minus 0.5. So this signal is having these three components. So we can say it is a line spectrum, it is a discrete spectrum, it is having only few components. Now we are coming to our main topic, Fourier transform. And you see here, I have shown one signal x of t. This is not a periodic signal. And for periodic signal, we have defined the time period. As time period is defined, we can find the fundamental frequency, and using Fourier series coefficients, we can show that this signal can be decomposed in terms of sinusoidal components with fundamental frequency and its harmonics. But this is not the case here, because for this signal, time period is not defined. It is not periodic. So we can't have any fundamental frequency. Thus, there is no point to find to use Fourier series. Okay. But Fourier series for this periodic signal, you can notice that xpt can be decomposed in this form, exponential form, summation of Cn e to the power j n omega naught t, where Cn is given by 1 upon t naught, and this term is xpt times e to the power minus j n omega naught t dt. This is exactly the correlation between xpt and e to the power j n omega minus j n omega naught t. Okay, so to find out the coefficient of that term, we need to take correlation between xpt and this one, right? Now, for this Fourier transform, where the signal could be periodic or could be aperiodic, if it is basically aperiodic, then time period is not defined. In that case, what we will do? So as time t0 is not defined at all, okay, and one thing we can guess that, suppose if we consider this signal will repeat after infinity time, then obviously we can consider it's a periodic signal. Okay, so this aperiodic signal could be considered as a periodic with the concept that time period t0 is infinite. If I consider t0 is infinite, then this omega naught is going to be 0, because 2 pi upon t0 is becoming almost 0. So means that the frequencies are very, very close. Okay, all the frequencies are very close. So what we'll do, we'll not consider this t0, because t0 we may consider very high. So I'll try to take the correlation between this xt with all the frequencies, means e to the power j omega t. Omega is continuous variable, any frequency. Remember, here the frequencies are integer multiple of omega naught, but here omega naught does not exist. So I need to consider all the frequencies, all frequencies. Could be 1 Hz, could be 1.5 Hz, anything, right? All the frequency we will consider, and then we'll take correlation between xt and that frequency exponential signals, and this one, and we'll ignore this 1 upon t0, because t0 is not possible to know, because t0 is becoming almost infinity. 1 upon t0 will become 0, then everything will become 0. It is useless. Okay, to avoid this thing, we'll ignore this term 1 upon t0. Just I will consider this term xt e to the power minus j omega t. It will give you the correlation between xt and that frequency omega, sinusoidal signals or complex exponential signals, right? So these I'll call it as x of w, which is function of w. Okay, here this one xt2 x of capital X of w, this is considered as Fourier transform. Now we'll try to understand this thing in detail. Okay, what is x of w? How it will give you the sense of frequencies. And you see here, this signal is having some undulation, means some frequency is there. If it is changing very rapidly, then that signal will contain higher frequencies. And if signal is changing slowly, we can guess that signal will contain low frequency, right? Now I'll consider this signal, this f. So this is one cosine form, but it will exist within -5 second to +5 second around 0, and rest of the time it will 0. So is it a periodic signal? No, this is not a periodic signal because it does not refit. So this is a periodic signal. I'll define this signal as x of t equals to cos 2 pi t for this time range minus 0.5 to 0.5, otherwise it is 0. So this is the signal, and for this signal we can compute this one, x of w minus infinity to infinity x of t to the power minus j omega t. And now consider that this signal is an event signal. As it is event signal, we can expect that the frequencies could be cosine, because sine components are odd signals, cosines are only even signals. So this signal will have only cosine terms. So in this exponential form it will be power j omega t. So if I ignore that thing, so correlation between cosine and xt will be there, but xt with the sine, that part will be 0 or will vanish. So I'll consider only this one, this cos 2 pi t into cos omega t dt. Sine term I am not going to consider, and this integral will compute, right? Now from MATLAB, this simulation result we have received. So what is the meaning of this? Here I have plotted the absolute value of x of w versus this frequency. Okay, so here I have considered linear frequency so that you can understand clearly. Okay, we can plot also with respect to angular frequency omega. So linear frequency in hertz I have shown here. So you can notice that this cos of 2 pi t, if it is repeating its shape, okay, then it will become a periodic signal with the frequency 1 hertz, because 2 pi ft and f equal to 1. But this is not periodic because this is 0 beyond 0.5 and it is also 0 less than minus 0.5. Okay, but for this one we have got this amplitude spectral. Okay, so what is the meaning of this? We'll try to understand this thing. So this integral, after this one we have got this function, its amplitude function is these things. Okay, so let us try to understand these things. Now what is x of 0? Means that omega equal to 0. How to compute this thing? So when omega equal to 0, this cos of 0 is 1. So just we'll take the integral of cos of 2 pi t dt over this time minus 0.5 to plus 0.5. And meaning is that integration is nothing but area under the curve. So this is a signal and its area we need to compute. So this is the area. So you can notice that this positive half is having the positive area and negative half will have negative area, but total area will cancel each other's. Okay, total area will become 0. So positive and negative will cancel, so total area will become 0. Thus x of 0 equal to 0, and it is signified here. You see that at 0 frequency, omega equal to 0 or f equal to 0, okay, the magnitude is 0, right? Now what about omega equal to pi? And omega pi means what is the f? F is 2 pi f. So f is nothing but omega by 2 pi. So 2 pi by 2 pi means pi cancel out. F equals to half. Half means 0.5 hertz. So when omega equal to pi radian per second, same thing is that linear frequency is that time 0.5 hertz. So at f equal to 0.5 hertz, we want to compute its magnitude. So how to compute that one? So what I'll do, I'll consider one signal, this cos 0.5, this is pi t, cos of pi t only, or 2 pi into 0.5 into t. Okay, this signal first we will multiply with these things and then we'll take area. So this cos of pi t is this green one, right? This is your cos of pi t. So we'll multiply these two signal, this green signal and this one, then resulting signal there will take the area under the curve. Okay, now as you notice that this blue one, this original signal cos of 2 pi t, it is valid only for minus 0.5 to 0.5 outside 0. So outside this one, if anything is multiplied, then also it will become 0. Thus you can see the product would look like this. So it will become 0 this side, and here we'll get this type of shape, and we can find the area under this curve like this. So you can notice that this green one is positive area and this two negative area, and total area could be something positive. Okay, meaning is that at omega equals to pi or f equals to 0.5 hertz, here something positive value we will get it, right? Now, what is the value of x of 2 pi? That is the Fourier transform at omega equal to 2 pi. Now you can see that this omega equal to 2 pi means this cos of omega t and this original signal cos of 2 pi t for this duration, they are exactly matching. So we can expect that it will give you the maximum coefficients, means maximum correlation. Okay, now we'll try to understand this one. Look at the figure. So I have drawn this green one. Green one is cos of 2 pi t periodic signal, and the blue one is the original signal that is within minus 0.5 to 0.5. That region we have this signal. So here it is overlap. So now if I have a product of these two, then we'll get only non-zero value within this range, and its shape is like this. And you can notice that here everything is positive. So now total area under this curve will become like this. As all are positive, total magnitude will be something positive, and that much is here. Okay, so what you can understand that in this one, if I consider a higher frequencies, suppose omega equal to 10 pi, then obviously you can expect that its amplitude, the Fourier transform of this amplitude will reduce, because this frequency is very high, and that frequency will have less correlation with this cos 2 pi t. So what happened? Actually from 0, earlier correlation was 0, then as omega is increasing a little bit, then its value is increasing, then it will attain the maximum value at omega equal to 2 pi. That means at 1 hertz it will have a maximum correlation, and beyond that, as frequency is increasing further, then its correlation is reducing, and at very high frequency it should have very low correlation, and that we can show like this. So if I plot this omega equal to 10 pi, means it will for this cos 10 pi t, this 5 hertz signal, this green one, and now if I take the product of these two, then it will look like this one. Now in this composite signal, this product signal, now there you will see the fluctuations are there, but it is even symmetry. So, and here you will see that positive and negative, they are almost cancelling each other's, and total area is going to be almost 0. It's very small. So as the frequency is increasing, the amplitude is reducing. Okay. Now the same thing I'll show here, but with bigger window size. So I have considered here is from minus 10 to plus 10. Earlier we had considered from minus 2 to plus 2. Now the same signal I have plotted here, and this is the corresponding Fourier transform. Now I want to add more pulses. Okay, this is only one pulse. If I add one more pulse or many more pulses, then every time we will be adding more pulses, and we want to get a corresponding to total cosine waveform periodic signal. I want to see how Fourier transform is changing. as we are adding more number of pulses. Just look at this one. So if I add one more, means now window size is, so non-zero value will start from -1 and maximum is +1. Within that we have 2 pulses, right? And you can notice here that this part is reduced, greatly reduced, means the frequency near to 0 DC and that amplitude is reduced greatly, and also the side frequency above this 1 Hz is also reducing. Okay, you notice further, again it is becoming sharper. This part, it is more sharp about this f equal to 1 Hz. At 1 Hz signal, it is magnitude is now 1.5. Further, it is becoming sharper. So just this axis, pay attention about this axis. Axis is changing. This, okay. So this value is now around 2. Further it is. So you can notice that this is becoming sharper, right? So as we are go on adding these pulses, it is becoming almost one vertical line. Correct? So this is, so -10 to +10 I have considered. That time I have obtained this kind of Fourier transform. It is almost one straight line kind of thing. But some other side frequencies close to 1 Hz, they are having certain correlations. They're not exactly 0 correlation, because this is still, it is not a periodic signal, because I have shown -10 to +10. In MATLAB, if I compute this thing, then it will be considered as a finite length signal. And any finite length signal cannot be a periodic signal. Periodic signal is always infinite length signal. So if I increase this length from here, suppose -1000 to +1000, then we will get very sharp and side frequency will be reduced. This strength will be reduced. Okay. Here you can see that as number of pulses are added continuously, this height is increasing gradually. Okay, and it is going larger and larger, and it is also becoming sharper. Now I'll consider one complicated signal, and can you identify its shape? So this will look like one sine wave here and some fluctuations there. So exactly it is x of t is 2 times sine of 4 phi t plus 0.5 times sine of 14 phi t. Within, it is valid within -0.5 to 0.5. And other side, this side it is 0, this side also 0. Now we want to understand the Fourier transform of this signal. Now as it is having these two sine components, so we are expecting there should be some 2 peaks in this Fourier transform. And you can see here this MATLAB simulation result. So this is the Fourier transform of this signal, and remember this signal is from -2 to +2, and it is finite within -0.5 to +0.5. And in this, from this figure you can notice that at this frequency, and this frequency is 2 Hz corresponding to the sine 4 pi t, at 2 Hz its peak value is maximum. It is having one peak. Okay, another peak we are getting here, and that is corresponding to 7 Hz for this signal sine of 14 phi t, but its amplitude is 0.5, and whereas the sine of 4 phi t, its amplitude is 2. As its amplitude is 2, its peak is larger and its peak is smaller. And if you take an exact ratio between these two, here this peak value is 1 and here peak value is 0.25. So here you see the ratio 2 upon 0.5 means 4:1. So here also we are getting same 4:1 ratio. Okay. Now you can see that as we are adding the pulses, then this value is increasing, both the one. The one is corresponding to this 2 Hz, other one is corresponding to 7 Hz. Their corresponding amplitude is increasing. That as we are increasing this number of pulses, it is becoming more periodic, but its amplitude is going further and it will become infinite for infinite length duration. So what we have obtained that if I have one cosine signal, any cosine signal xt equals suppose cos of 8 pi t, its frequency is 4 Hz. This signal I have shown here -2 to +2, and if I compute its Fourier transform, then it should select only this frequency 4 Hz ideally, if it is perfectly cosine signal. I am not considering it is limited from -2 to +2, that's only I have shown, but it is exactly cosine signal, is a periodic signal. Then its ideal Fourier transform should look like this, because its amplitude will become infinite at f equal to 4 Hz. So I'll show it, we can show it by one arrow, okay. And similarly in the negative frequency, negative side, we can have these things. This negative frequency we are getting because of this exponential form, because exponential form we can have both positive and negative, okay. So we'll get these two impulses. This is called impulse, and this is denoted by delta function, a direct delta function. So we can write this is delta function f delta of f minus 4. It is located at f equal to 4. Its amplitude is infinite at f equal to 4, okay. But this total amplitude of this xt is now splitted in these two frequencies. Thus this coefficient we'll consider as half. Mathematically we'll consider this is half, okay, half delta f minus 4, and it is again half delta f plus 4, right. I wish to stop here, and from the discussion we are having following important conclusions. Fourier transform provides frequency content of both periodic as well as aperiodic signals. We can apply Fourier transform for both the cases. It could be for periodic as well as aperiodic. For aperiodic signal, Fourier transform is having finite amplitude spectral, and this is because we have removed this 1 upon t from this Fourier transform concept that you have seen there, and because of this now it is becoming finite. But for a periodic signal, for infinite length signal, this Fourier transform is having direct delta function in spectral, indicate that its function is becoming infinite, and it is because of the same reason that 1 upon t0, that part we have removed from Fourier series. Hope this video is useful to you, and if it is really useful, you may just press a like button, and if you have not yet subscribed this channel, you may subscribe this one if you wish to get more videos from this channel. Thanks for watching.